engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the programme where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith, and with Harry Lewis.
This week, the new COVID variant spreading internationally. What do we know about it so far? Have scientists found a new ninth planet? And if that wasn't enough for you, we hear how a project to print bacteria could help us to live on Mars.
Plus, plastic fantastic or plastic drastic problem? We put plastic under the microscope to find out what is good and what is bad about one of the world's favourite materials. The World Health Organization have given it the name Omicron and labelled it a variant of concern. It's a new COVID-19 variant spotted first by scientists in southern Africa, and it's spreading internationally.
The Health Secretary Sajid Javid says scientists are deeply concerned about a new variant of coronavirus that's been discovered in South Africa. Mr. Javid said the variant may be the most infectious yet.
Many countries have put in place control measures, and in the case of the UK, that means reintroducing screening for some travellers, face masks will make a reappearance for public transport and shops, and quarantine for the contacts of Omicron cases.
With us to explain what we know so far about the new variant and the next steps scientists are going to be taking to understand the scale of the threat is Sharon Peacock. She's a medical microbiologist at the University of Cambridge and she leads COG UK. That's the group responsible for sequencing the genetic codes of the COVID-19 cases we're diagnosing here in the UK so we can track variants like Omicron. Sharon, first of all, how was this picked up in the first place?
Hello, Chris. Nice to be with you today. We only need to go back about 12 days ago when cases in South Africa, they numbered 273 actually for the day, which is quite low. Actually, it's very low recorded numbers. But actually what happened after that was that there was a rapid rise noted in cases. So 3 days ago, there was more than 1,200 cases. And yesterday, there were more than 3,000 cases. And so it's the rate of rise that really alarmed the Ministry of Health in South Africa. And when they looked to see where these cases were arising, it was in one particular part of South Africa called Gauteng province. And so what the Ministry of Health and scientists did was to target genome sequencing of positive samples from people living in that area. And that is how they identified a new variant not seen before, which has a numerical name, B11529, but which the WHO have gone on to call Omicron.
Obviously, the genetic code can speak volumes about the likely behaviour of a particular viral variant. When you look at the genetic code of this new variant, are there any illuminating features?
Something that is very striking is that this is the most mutated variant that we've seen today. It's got around 50 mutations in the entire genome, but about 30 of those, just over 30, are really focused in this spike protein. That's the part of the virus that interacts with the human cells as it's kind of gaining entry into the cell. So we know that that spike protein has got a large number of mutations, more so than previous variants of concern, actually. And several of the mutations we've been able to identify have been seen in other variants of concern that have been linked to increased transmissibility and immune evasion. But there are actually a lot of mutations in this new variant where we don't actually know whether they'll alter the biology of the virus or not.
Why would genetic changes in that spike region make us worried? What could they do to the spike which would mean that the virus is either worse, more transmissible, or does things with vaccines?
A change in the genetic code or a typo can actually lead to a change in the amino acid, which is the building blocks of life, and then change the way the virus structure is. And that change in structure can change the way it interacts with our cells. So it could mean that the interaction with the receptor that it needs to bind onto in the human is better. It could mean that the virus is better able to replicate in cells. So there is a range of ways that the virus can become fitter, if you like. And it's those mutations that really change the building blocks of the virus and the way it interacts with us.
And is there any evidence yet from talking to the doctors looking after these 3,000 plus cases in Gauteng in South Africa as to the behaviour of the virus? Is it any worse? Is it the same? Is it different to what we're seeing with the Delta virus, which is the dominant variant we've got around the world at the moment?
Certainly, clinicians that are treating these particular patients, they've said that they think that they have different sets of symptoms and that their symptoms are less severe. But I think we have to be quite cautious about whether that information is relevant to the UK. The demographic of that region is that the population are younger overall. They have a lower rate of vaccination of the population. So the vaccination for 2 jabs, full vaccination is 24%. And I think that we have to be cautious about whether this is going to cause, less severe disease, the same severity of disease, or even, at the other end of the spectrum, more severe. So we need to do studies very urgently to identify whether these kind of anecdotal observations are actually the case in the UK.
What experiments do we now need to do then in order to learn what threat this does or doesn't pose to us?
Well, there's 2 types of things that we need to do. The first are the experiments in the lab. So we need to look at whether the virus is so-called neutralized by antibodies, i.e., if we have antibodies to the virus, are they kind of less effective at kind of coating the virus and really making the virus less able to interact with our cells? So neutralization assays we need to do, and other types of lab experiments to see how this virus interacts with our cells. But the really important studies are also real-world studies. So we need to see whether this does cause a different type of severity of disease by actually observing a severity of disease. We need to look at whether people who've had infection, natural infection before, or vaccination are going to be infected with this particular variant or not. So these are kind of the critical real-world studies to look at whether vaccination efficacy and disease severity are affected in any way.
Sharon Peacock, thank you very much.
Now for something a bit different. Since the demotion of Pluto from a planet to a dwarf planet back in 2006, our solar system has had a vacancy for a 9th planet. We have reason to believe that this does exist, but no one as of yet has ever seen it. Well, perhaps, until now. Astrophysicist Michael Rowan Robinson from Imperial College London has been looking through decades-old data that had previously been thrown into the proverbial trash pile. And he's discovered a mysterious object that he reckons could be a new planet.
I set out to find the postulated 9th planet, which has been proposed to explain the motions of dwarf planets in the outer solar system.
The search for the 9th planet. It sounds just like the plot of a sci-fi novel, but it's something astrophysicists are very seriously looking for. I'm sure you are all as deeply as upset as I was when Pluto was demoted from planet to dwarf planet status in 2006. But that was because physicists realised that there were thousands of these Pluto-like objects, or planetesimals, flying around in this part of the solar system. Meg Schwamm from Queen University Belfast studies these objects and explained that something in their behaviour just isn't quite right.
There's sort of a set of planetesimals that have been recently discovered that seem to be all aligned in being found in one part of the sky. For that to happen, there needs to be a big mass still around in the solar system. I like to think of it like sheep. So the sheepdog, right, is keeping everybody in line. That's led people to really think about this Planet 9 theory that's been proposed as, can we find that sheepdog? Should we go look?
This question of is there a 9th planet that we don't know of yet has been puzzling astrophysicists for a long time. For Michael, it's perplexed him for decades.
So I have been interested in the idea of a planet in the outer reaches of the solar system actually since 1983. So in 1983, I was working on the IRAS space mission.
This IRAS satellite looked for objects in the infrared range, looking for the tiny amount of heat given off by distant objects. At the time, everyone thought Planet 9 would be a large planet at the furthest reaches of the solar system, corralling all of those little planetesimal sheep. But after failing to find any good candidates in the data, Michael wondered, what if Planet 9 isn't far away? What if it's just small? With these new criteria in mind, Michael looked through all of the satellite observations that had previously been discarded.
So I was left with, again, about 100-odd cases. And again, I eliminated most of them. And I was just left with this one case, which I still can't rule out. So that is my candidate.
So does that mean it's a planet? What are the chances that it's a planet?
That's an interesting question. It's about the right sort of distance. It's about the right sort of mass. It's extremely close to the plane of the Milky Way, which makes it very difficult to observe. And also it makes the detections that I have doubtful, because it could be that they are just interstellar dust. But as I say, it's there. It's the best that I could find in this vast search.
If you were a gambling man, how likely would you say this was another planet?
I vary from moment to moment and day to day. When I drafted the paper, I said, I suppose the reality of this is perhaps 50%.
That's not bad.
Some days, yeah, but some days I wake up and think it's 1%. So I just don't, I can't say.
And what do other scientists think? Could this mystery object be the 9th planet physicists have been looking for so long? Meg Schwamm.
I don't think there's enough evidence to say it is. I think it's interesting. If it's real, we hopefully will be able to detect it with Rubin Observatory and see it moving in optical wavelengths.
That was Sally LePage speaking with Meg Schwamm, and before her, Michael Rowan Robinson.
From baffling British weather
The sideways spines of the vertebrae coming off here
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Still to come in this hour, we find out why it's been such a big year for certain species of fungi, and we also visit one of the largest animal shelter charities in Europe, but maybe not for the reason you might expect.
Well, now for something completely different. Do you remember that Robin Williams movie Flubber? Well, if you didn't see it, it's about a wacky green jelly-like substance that comes alive and then starts bouncing around, breaking everything it encounters. Luckily, that is not the direction the authors of our next story chose to go in, but the team at Northeastern University have successfully genetically programmed bacteria to secrete a printable jelly-like ink that can be used in a 3D printer. The gel they print isn't green, and it doesn't bounce around crazily against the walls, but it is alive because it contains living cells that can release therapeutic drugs or remove toxins from their surroundings. Jacopo Russo heard from creator Neil Joshi how it works.
It starts with genetic engineering of E. coli.
Is that the bacterium we have in our intestines?
Yes, it's found in your intestines and in soil. We introduce new genes that didn't previously exist in E. coli, and then we tell the cells when to produce a customized protein polymer that would assemble in multiple dimensions. The individual protein is like a building block, a bead, and that bead is going to assemble into this fiber like many beads on a string. And then that fiber will in turn bundle into larger structures.
Okay, and what does it look like in practice? If I entered your lab, what would I be looking at?
You would be looking at a lot of bacteria growing in an incubator. We load the material that comes out of those bacteria into the 3D printer setup.
When you say 3D printers, do you mean the ones that some people now have at home?
Yes, very similar to that. The only difference is that our mechanism of printing doesn't involve heating. We designed the material that we made so that it is firm enough to hold its own weight when it's resting. But then when you apply pressure to it, it will flow like a liquid. And I think everybody's familiar with this concept in the form of toothpaste, which is stuck in the tube. It will flow if you apply pressure. So we designed our material to have similar properties. And then we use pressure to do the printing rather than heat.
What kind of things have you made? What does it look like when it comes out of the printer?
Like a clear gelatin-like substance, like Jell-O with no food coloring in it. It's composed of our engineered cells and the custom protein polymer that they produced.
But Jell-O is dead in a way. There's no living thing in it, whereas your material has living cells in it.
Correct, yes.
What can these cells do?
We can not only program the ability to make the ink into the cells, but we can also introduce other features that you might find in a living system. Cells that can respond to their environment. For example, they could release some drug, or they could bind and remove some pollutant from their surroundings, or they could even undergo a process of cell suicide inside the material if we wanted to limit the spread of those cells into the surrounding environment.
Right, because this thing is alive and it's made of microbes, and usually we want to defend ourselves from microbes, whereas you've created something out of microbes.
We are certainly careful to use only non-pathogenic lab strains, and I think that this is a realistic way to make materials in a scalable manufacturing context. It's already done in some cases, with insulin perhaps being the example that's been around for the longest.
This already sounds like science fiction, but what's the wildest application you could envision for the future?
One of the things that's kind of obvious as a place that this could be particularly useful is for building structures in space. Organizations like NASA have already started planning for how they would build structures and habitats in extraterrestrial environments.
So we're talking about when we colonize Mars, for example.
Yeah, Mars or the moon, or perhaps on a space station. And in all those contexts, 3D printing comes up repeatedly as a very versatile way to make multiple different buildings or structures or basically whatever you want. Problem with that is that it would be cost prohibitive to ship tons and tons of plastic for using a 3D printer. You would need a way to make your printing ink locally. The way to do that is really with microbes. You could take a few microbes with you in a small vial and then kind of make what you needed from those microbes.
Isn't that amazing? That was Neil Joshi from Northeastern University, and the study was published in Nature Communications.
Now, this summer and autumn, as if we didn't know it here in the UK, we got a lot of rain. Now, that was, of course, terrible news for anyone who'd booked a staycation like me. But it's been a bumper year, on the other hand, if you're a fungus. Certain species of fungi are flourishing, and Jassy Drakulic from the Royal Horticultural Society told Harry Lewis what you might have seen sprouting out of your garden.
At the Royal Horticultural Society, we have a members' advisory service where people send us in pictures of things that are going on in their gardens and ask for advice about them. And one thing that we've noticed this year is that we've had 76% more inquiries about saprophytic fungi, ones that grow on dead material, than we did last year. It's usually with the angle of, what is this? I'm afraid of it. Is it going to cause harm? How do I get rid of it? And we're trying to kind of educate them to say, well, and there's very few things that are out there that are going to be causing any harm to your garden. And the overwhelming majority will be doing a good service, either by rotting down dead material. This is the type that we've seen so many more of being sent into us this year. And in doing so, that liberates the nutrients locked up in that woody material.
What are people seeing more of in their garden? What species, and how do we identify them?
So I think on a sort of a mass level, I've seen so many more ink caps coming in this year than I have before. And ink caps are really wonderful because they're very varied. But what they all do is, after the mushrooms have formed, they then deliquesce, which is sort of a fancy word for dissolve, and turn into black ink, which are droplets of spores. And these can range in size from really robust, shaggy ink caps, which kind of, I think they look like a big white club when they're first growing out, and they're all kind of flaky and hairy on top and reach over a foot in height. And then on the flip side of things, you have the very dainty, delicate hairs for ink caps. So again, they start off as this little hairy foot that comes up on a tiny stalk, and it's only there for a few hours in the day, usually from the dewy morning, and then by lunchtime they're gone. And they're just so fleeting and so delicate. I think they're just really charming.
You painted a fabulous picture there, Jassy. At the moment, with years to come, are we expecting different fungi to pop up in different areas? Are we expecting more fungi in general?
Well, the fruiting season for fungi has increased dramatically over the last 30 years, we think, because of the changing climate. And that's affected different groups of fungi in different ways. So when we look at the wood rotters, it seems like there's more of those species that have increased their fruiting season. So you'll be seeing them earlier in the year and also for a longer time during the autumn. In contrast, things like the mycorrhizal fungi, so those that associate with the roots of plants and help them take up nutrients and water, their fruiting season seems to be shortening.
And we've come to what feels like the end of the fungi season. Am I right in saying that as we go into winter, is there anything that people can be looking for or harvesting sustainably?
So the jeweled amanita, that only really comes up once the first frost has hit, and it kind of signifies that winter is coming. Even honey fungus really prefers the later part of the autumn. And then there's some more friendly wood-rotting fungi that are also edible, like the oyster mushrooms that do quite well throughout the very cold spell. And whilst these are edible, we'd always make sure people, if they are going to go out and look for things to eat, that they do so responsibly, not just for their own health, but if you are picking things, not to completely clear cut everything that is there, and just to take a few specimens for your table, to have a chance to spread their spores first.
And you can send a snap of any odd species that you have come across to us at chris@thenakedscientist.com. You can also tweet @nakedscientist. And if you do, we will give you a hand at trying to identify what it is that you have snapped. Thanks very much to Jassy Drakulich there.
Now, Christmas is on the way, and as the old saying goes, your eyes are often much bigger than your stomach. Certainly true for many of us over the festive period. But it turns out that a miscalculation in a set of nerve cells in the brain's appetite and reward system could be what triggers overeating. Julia Ravey spoke to Nick Betley at the University of Pennsylvania to hear what he has in mind.
Because of these highly caloric, highly palatable foods, people end up eating just a little bit more food than they should every day. And by eating just a little bit more food every day for a long period of time, you put on a lot of weight. So in our study, we took advantage of the fact that there are people who have a genetic disorder known as Prader-Willi syndrome, that one of the consequences is they have an insatiable appetite. And so we reasoned that they must be missing a neural signal for satiation in the brain. There must be something different about their brains from everybody else's. And so we compared neural activity in the brain of individuals with Prader-Willi syndrome to individuals who don't have this syndrome. And it turns out that in control subjects, the cerebellum is activated by food cues and hunger. And Prader-Willi syndrome individuals are completely missing that cue.
And how did you find out what this region of the brain does?
The cerebellum is typically known for being involved in motor function and coordination, but never before had the cerebellum been implicated in food intake and food intake control. And so based on finding this signal in Prader-Willi subjects, we transitioned our research to rodent models where we could go inside of the brain and manipulate neural activity. We found a subset of neurons in a very discrete region of the deep cerebellar nuclei that, when activated, actually limit the animal's meal size about 75% in that individual meal.
And did this alter the behavior of the mice in any other way?
We know that the cerebellum is involved in a lot of other behaviors, specifically things like motor behavior. So we were worried that maybe the animal wasn't eating as much because the animal wasn't moving as well. And so we performed a series of experiments to make sure that motor function was intact. So these animals can run on a rotarod like a normal animal.
Do you think the mice where these cells were active, do you think these mice enjoyed their food as much?
What we found is that the cerebellum is actually interfacing with the reward system to reduce the reward value of additional consumption. And so this would be like you stopping eating, peas and rice because you've had enough of food and you're homeostatically sated. But if your cerebellum were active, it would reduce the reward value of even things like chocolate cake.
Do you think these cells might operate in a similar way in humans?
So yeah, that's what we think is so exciting about this study. We started with a human task-based fMRI study. We went into the mouse brain to identify the precise neurons, to understand every molecule in these neurons, to try to understand how they influence the neural activity in other regions of the brain. But now that we've understood all that, maybe we can pull back and go back to the humans and see if activating these neurons in the human brain will actually reduce meal size. And so could you imagine if we could develop a hat with some magnets in it that you could put on before you eat your meal that reduces the size of your meal by, say, 25%, and you just eat a little bit less every day without feeling hungry? This would be a great way to lose weight. So maybe that piece of chocolate cake at the end of your meal will be slightly less palatable, and maybe you will have a smaller piece of chocolate cake. So you'll still be able to enjoy life. You just won't eat past your homeostatic checkpoint.
Do you think these results can help change the stigma attached to obesity?
I think it could change the stigma attached to obesity and other neural disorders in general. I think knowing that food intake control is regulated by neural circuits in the brain, and that the activity in these neurons that is independent of an individual's willpower is actually controlling or modulating how much food an individual eats is powerful information. And so by better understanding how these circuits work, we have the potential to really change the way people think about obesity and really understand it as just another type of disease, just like as if you had a heart disease.
So there you go. You pull a cracker over your Christmas dinner, out pops an appetite-suppressing party hat. What a win. Nick Betley, whom you just heard there, just published that study in the journal Nature.
Much has changed for business owners, managers, and staff recently. But with over 30 years' experience in telecommunications, award-winning independent company Spitfire have the expertise to make sure you stay ahead and can keep on innovating. Whether it's connectivity, MPLS networks, firewalls, or phone systems, Spitfire can help. To find out more, go to spitfire.co.uk. That's spitfire.co.uk. Spitfire, telecoms and IP engineering solutions for business since 1988.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
For the rest of the show this week, we have naked scientist, intern and materials engineer at Cambridge University, Werner Vesainen. We've tasked him with running a critical eye over something that has undoubtedly revolutionised the world of materials science and given us all kinds of conveniences. But that doesn't mean that it's without fault. It's made from oil. It turns out to be a big source of greenhouse gases, not only during manufacture, but also when it begins to break down. As you've probably guessed, this week we're looking at the two sides of plastic. So will Werner's verdict be plastic fantastic or plastic drastic?
On my way home from work tonight, I'm going into my local supermarket in the centre of Cambridge to pick up some ingredients for my dinner. I'm planning to make some spaghetti bolognese. So on my shopping list are some mince, fresh tomatoes, carrots, garlic, onions, celery, and of course some spaghetti. Okay, here we go. I got my mask. I'm entering the supermarket. Let's see if I can get everything on my list. Got my basket. Okay, I'm in the vegetables aisle now. Let's see what I can find. Okay, found my first ingredient. Got some celery and some plastic. Found my next ingredient. We got carrots and plastic. Found me some tomatoes. Also nicely wrapped in plastic. Some onions, still plastic. Final vegetable, garlic. Again wrapped in a plastic fleece. Now that I've got all the vegetables, I've come around the corner to look for my mince, and I picked one up. Every single one was wrapped in plastic. In it goes. Okay, I'm in the pasta aisle now, looking for my spaghetti. Bottom shelf, here we go. Spaghetti and plastic. It's a plastic full house. All this plastic packaging has really got me thinking, can we live without plastic? Would using less plastic reduce my carbon footprint? Could cutting my plastic consumption help address the climate crisis? While I finish the rest of my shot, let's investigate this further. David Attenborough opened our eyes globally to the challenges presented by plastic pollution and the effect it has on our marine ecosystems.
We hoped that Blue Planet 2 would open people's eyes to the damage that we are doing to our oceans.
In fact, we release 15 million metric tons of plastic every year into our oceans, and that's equivalent to the mass of more than 1 million double-decker buses. And that's the only issue with plastic, right? That we produce too much of it and it has to go somewhere, so we end up with a lot of waste. Well, no, not according to Judith Enck at least, and her new bombshell of a report.
What a lot of people may not realize is the intimate connection between plastic production and climate change. So my organization, Beyond Plastics, issued a new report called The New Coal: Plastics and Climate Change, where we detail the connection between plastics and greenhouse gas emissions.
And what did you find exactly in terms of the emissions from plastics?
It is significant. Overall, the report found that the US plastics industry is responsible for at least 232 million tons of greenhouse gas emissions into the atmosphere every single year. 232 million tons is the equivalent of the greenhouse gas emissions coming out of 116 average-sized coal-fired power plants. And then we looked ahead as coal plants continued to close and the plastics manufacturing infrastructure expands in the United States. The plastics industry's contribution to climate change will exceed that of coal plants in the United States by 2030. We found that plastics is the fossil fuel industry's plan B.
How did you go about calculating the emissions?
Most of the data actually comes from the plastics industry and is reported to federal agencies. We relied a lot on existing data. We just did the hard work of pulling it all together.
So could you go through the different steps and outline the emissions associated with each and how they come about?
You have to look at production, use, and disposal. So we looked first at fracking. Basically, it's a new cheap way to access gas. What happens at fracking sites is large amounts of water and chemicals and sand are injected underground to basically shake up the underground area. So gas is released through fissures in bedrock. The gas is brought up to the surface and then captured as an electricity source. Part of that process includes flaring of ethane into the atmosphere. And ethane is a potent greenhouse gas. And so flaring it is not good. But what we're seeing in some select areas is capturing that ethane and sending it by pipeline to these ethane cracker facilities. And that's why there's such an increase in the use of plastic in the United States. It's because of hydrofracking. And on the fracking step, the amount is about 36 million tons of greenhouse gases a year. And that's roughly equivalent to the release of 18 average size coal-fired power plants. And then the real big one we examined was ethane crackers. These are central players of plastic production where fracked gas is superheated until the molecules crack into new components. So you take the waste gas, you send it by new pipelines to these newly constructed ethane cracker plants, and they release roughly 70 million tons of greenhouse gases in 2020. And that's the equivalent to the release of 35 average size coal-fired power plants. However, the key thing on this point is that major expansion of these facilities is planned. And so we think that by the year 2025, we'll be looking at 42 million additional tons of greenhouse gases, which is the equivalent to 21 coal-fired power plants. We then looked at exports and imports. The ongoing plastic build-out in the United States is not just for US consumption. There are these very large tankers. A tremendous amount of ethane gas is shipped by tanker to cracker facilities in India, China, and Europe right after it's extracted from beneath the state of Texas. And that is all to create single-use plastic packaging.
So how do you attribute these emissions to plastic if it seems that the ethane is a byproduct of getting this gas out of the ground for electricity?
Well, because the ethane that is captured and sent to ethane cracker facilities is to create more single-use plastics. We're not saying in the report that all of hydrofracking is associated with plastic production, because as noted, a lot of it is used for electricity generation. But there's this unknown element of fracking that links it to plastic production. And because there's a glut of fracked gas on the market, we're seeing more and more of this gas being used to make plastics.
Can you make plastics from other fossil fuels?
Yes, historically, plastic was made from chemicals and oil, and now it's made from chemicals and fracked gas.
So any fossil fuels, you can turn it into plastic one way or another.
Yes, and oil is a problem as well. Plastic production and fossil fuels are attached at the hip. You don't have one without the other.
That was Judith Enck from Bennington College, and you can find the report she was referring to on beyondplastics.org. Given how much is being invested to produce more plastic, and given the large amounts of emissions associated with them, it begs the question, why do we have so much of it in the first place? I spoke to Nicola de Blasio from Harvard University to find out more about what makes plastic such a useful material.
From a chemical point of view, plastics are made of one or more polymers. Basically, they are long chains of carbon atoms. and include well-known names such as polyethylene, which we use in food packaging, automotive parts, and even banknotes, or polyethylene terephthalate, PET, which is used in plastic bottles.
Why do we have so much plastic in the world today?
We have so much plastic because plastics have enabled modern life as we know it. Plastic is so ubiquitous in our daily lives that we do not give it much thought. Yet it is everywhere, from clothing to chewing gums, from tea bags to whitening toothpaste, from toys to plastic bottles. Just to give you an idea, up to 5 trillion single-use plastic bags are consumed every year, and 1 million plastic water bottles are sold each minute around the world. However, the lack of end-of-life consideration and the high cost of recycling have turned plastic into the victim of its own success and has created a global environmental crisis.
We have plastic everywhere in our modern world, but what is it about plastic that makes it so useful?
Because plastic are inexpensive, durable and lightweight. They can be soft and pliable or hard and strong. They can withstand extreme cold or heat, and they can be corrosion or chemical resistant. If the physical properties of the plastic that we produce do not meet the desired requirements, they can be enhanced with additives such as pigments, flame retardants, antioxidants, and so on.
Is it conceivable to imagine a world without plastic?
Well, we just need to look around us and the answer is pretty obvious. Today, a world without plastic is really almost unimaginable. Plastic has molded society in many ways that make our lives easier and safer, even more so during the COVID-19 pandemic. In the end, the real question is how can we leverage the advantages of plastic without contributing to the world's environmental crisis?
That was Nicola de Blasio from Harvard University. As Nicola said, we can modify plastics to fit the particular application that we need to use them for. Like this supermarket plastic bag made from polyethylene, which is soft and flexible but also durable, and has color added to it to give it its bright orange color. Or this case for my wireless earphones made from polycarbonate, which is strong and keeps my earphones well protected, but also likely has UV stabilizers added to it so that it does not break down under sunlight. Or this plastic box for my supermarket brownie pieces made from recycled PET, which is lightweight and also molded such that it has a closable lid, meaning that the rest of the pieces can be kept secured and fresh, even after I have made a start on them during tea break. That's not all. You can have plastics on a far grander scale in some rather unexpected places. I bet one place you didn't expect to find them was in wind turbines. I mean, just look at the size of them. It's huge. Although we already heard that plastics are bad for the environment due to the pollution, but also the emissions they release, this is one application where they are helping to fight the climate crisis. Darshil Shah from the University of Cambridge took me to the wind turbine at the Wood Green Animal Charity in Godmanchester in Cambridgeshire to tell me why plastics are essential for structures like the wind turbine. Right, Darshil. We're standing right next to the wind turbine. Which parts are actually made of plastic?
Actually, the tower is completely made from steel, but it's the blades where all the composite and the plastic materials are.
And why are plastics used for the blades?
There are two key reasons why we have been making these out of reinforced plastics. Firstly, wind turbines become more efficient if the blade shape is particularly more aerodynamic. And to form these efficient blade shapes, you need to be able to curve them and taper them and twist them in very specific profiles, which is manufacturable through reinforced plastics. The other key advantage of composite materials is also their great strength and stiffness to weight ratios. So they're incredibly strong and stiff for their weight. And this is important because the lighter the blade is, the whole turbine more efficient in generating power, which is the whole purpose of a wind turbine.
You mentioned that these are not any old plastics. They're so-called composite materials. So what are composite materials?
In this case, we refer to them as reinforced plastics, and usually they are fiber reinforced plastics. So the polymer itself can be synthetically derived from petrochemical sources. In this case, it is based on an epoxy resin. The fibers themselves are what are actually providing the stiffness and the strength. In this case, it is fiberglass that is being used. So this blade is only about 25 meters in length, weighing about 1 ton to 1.5 tons. But blades can get much, much larger. So today's largest wind turbine is getting to about 14 megawatts of rated power, with the blades themselves being 4 times the length of this blade, but around 28 times the power capacity of this turbine.
So these blades are made of plastic, and we've heard that plastics have quite a lot of emissions associated with them. But also the wind turbines are providing us renewable energy. So would you say this is a good use of plastics?
I think this is definitely one of the more better uses of reinforced plastics. The two main areas where plastics are using a lot of energy and consumption in their processing is firstly to do with their petrochemically sourced nature, and these need to be converted into the polymer firstly, and then for the fibers, if it's carbon fiber, you need to process these at really high temperatures, and therefore a lot of energy going into the production of these high performance fibers, and they are reducing the amount of tower material you're requiring. So it is a good use of the resource, but we can do better.
It's a bit of a rainy and chilly day today. Should we move somewhere a bit warmer to continue the chat?
Yes, definitely. I'd like that.
So we've come away from the wind turbine because it was a very dreary and rainy day today. And to cheer us up, I bought both of us some donuts, which we're about to enjoy. And I wanted to run you through this analogy and see what you thought. So plastics to the earth are a bit like donuts to human health. We know that donuts are not very good for us if we eat too many of them, but they serve an important function because they taste oh so good. And a bit like how plastics, if we use too much of them, they end up in the oceans and cause a lot of pollution and emissions. So we need to be careful in the way that we use our plastics and use them in moderation, a bit like how we should approach eating donuts. What do you think of this analogy?
I think I can work with it. I like it. Just like we have donuts as a treat, I suppose we need to be more selective where we are using plastics. And if we think about it, plastics have really fantastic properties, and that's why we do use a lot of it. They keep things durable, and we need to get better at both considering end-of-life possibilities of these materials, as well as on the other scale, how can we make more of these from bio-based resources?
So coming back to the wind turbine blades, so we typically see plastic as a problem because it accumulates as waste, but this plastic in the wind turbines, it seemed to me, could keep spinning for many years. So why might this plastic represent a problem then?
Well, partly because wind turbine blades have a defined lifespan. Usually that tends to be 20 to 25 years, after which a wind turbine is decommissioned, it is completely brought down, and you just replace it with a new one. We consume, or at least produce, 2.5 million tons of reinforced plastic materials specifically for wind turbine blades every year.
How do these techniques for recycling reinforced plastics compare to the techniques used to recycle typical plastics you might see?
That's an interesting question, because the classes of the polymers that are used in reinforced plastics, particularly for wind turbines, and the plastics you get in packaging are different. So the packaging plastics fall in a category referred to as thermoplastics, which effectively, when you heat them, they start to melt, and then you can mold them into a specific shape. And when you take away the heat, it retains the shape. But amazingly, you can then reheat these materials and form them into a new shape again if you like. In contrast, the polymers that are used in wind turbine blades tend to be thermosets. And these initially start off as liquids, and then a polymerization process leads to a hardened and cured material, which is the shape that you end up with following molding. Thermosets are slightly more difficult to recycle because once they form this cured and hardened material, it's not a reversible process. So the only way to deal with them tends to be either incineration, landfilling is what is traditionally used. There are some methods in which you can reuse some of these polymers to downcycle, so integrate them for making injection molded materials, for example. The complexity of recycling becomes even more increased when you introduce fibers. It's related to the problem that we have in conventional products of mixed plastics. If you have too many different types of materials together, you need to first spend energy in separating these materials and then dealing with them.
So do we need to start making wind turbines out of thermoplastics to make recycling them feasible?
Again, that's a fascinating question. So there have been some efforts to make wind turbine blades with thermoplastics. And the challenge with thermoplastics is that they usually start off as solids, which you then need to heat up. And that's all and well if the component size is quite small. But if it's a wind turbine blade that is 25 meters long or 100 meters long, then that becomes really almost impossible, because then you need compression molding machines, so presses and heated presses that will facilitate the fabrication of these large components. And therefore, the possibility of making them with thermoplastics is quite small. Thermosets for a while will remain king.
Thank you so much, Darshil. This has been illuminating. Shall we head back to Cambridge now?
Yes, and have our donuts.
Yes, let's enjoy the donuts and then we'll be on our way. Those donuts were delicious, and the wind turbine was not half bad either. Thanks to Darshil Shah of Cambridge University and to Wood Green for giving us access to the wind turbine, which powers their entire site in Godmanchester, one of the largest animal rehoming centers in Europe, generating 500 kilojoules of energy every second, with some of that being fed back to the national grid for their profit. However, the discussion with Darshil also really brought home the point that these reinforced plastic blades are very challenging to recycle. Recycling regular plastics also appears to be a challenge, given that I came across a statistic from the University of California that only 9% of all plastics ever produced have been recycled. Given that plastics are typically a single polymer, what could be the reason for this? I spoke to Lee Bell from the organization IPEN, or the International Pollutants Elimination Network, to better understand why this might be.
Well, largely because there's no real market for recycled plastics. And the second issue is because of the problems associated with the actual composition of the plastics themselves. Most of them contain a variety of additives. Additives are incorporated into plastics to give them different colors, different textures, different flexibilities. When you go to process it through standard mechanical recycling processes, the problem is that the additives don't mix well, and even to that extent that different types of polymers don't mix well because they contaminate the resulting material that comes out. So even with something that's relatively easy to recycle, like your standard plastic water bottle, it can only go through a few repeat processes of mechanical recycling before it starts to degrade significantly. So there's no such thing as an endlessly recyclable plastic.
What would you say are the carbon emissions associated with plastic recycling processes?
Well, it varies according to the process. If you convert it to an oil fuel, which is what most chemical recycling do, you'd be looking at about another 200,000 tons of CO2 from that. If you look to incineration, and some people consider burning plastic in incinerators a form of recycling because of the energy recovery, you're looking at about 1.4 tons of CO2 for every ton of plastic entering that process. With mechanical recycling, you're essentially looking at the carbon emissions that result from operating the machinery. And so from a carbon perspective, mechanical recycling is the one that you'd want to support.
How would you say we can improve our rates of mechanical recycling?
Well, I think the first issue is that producers of plastic need to restructure their operations so that they remove a lot of the toxic additives that are causing problems in terms of preventing plastics from being processed in large amounts. But at a broader level, we have to look at economic incentives to prioritize recycling using mechanical means. And that means placing some sort of a financial tax or other mechanism on virgin plastics, because the cost of mechanical recycling is significant enough that it can't compete readily with virgin plastics.
And so, taking all of this into account, do you believe that recycling presents a solution to the plastic crisis that we face?
No, I don't. I think the problem we have is the vast increases in production of plastic. Mechanical recycling cannot cope with the vast increases. I think we're looking at something like quadrupling virgin plastic production by 2050.
That was Lee Bell from IPEN. If recycling is not the answer, then what should we be doing instead with plastics going forward? Fredrik Bauer from Lund University is an expert in plastics policy and recently published an article titled Plastic Dinosaurs. He sounds like my kind of researcher. I spoke to him to find out more about the future of plastics. We heard from Nicola de Blasio earlier about how plastics are everywhere in our modern society, but how did we end up in this position?
The history of modern plastics is one that really took off after the Second World War. So in the 1950s, the petrochemical industry emerged and identified plastics as a very interesting group of materials and really worked hard to find new ways of using plastics in many different domains of our everyday lives.
Are the fossil fuel and petrochemical companies just responding to consumer demand given how useful plastic is as a material?
I would not say it's fair to say that production is only responding to demand. Rather, there has been a very strategic effort to create demand and to shape demand in ways that really uses plastics to a very large extent.
Judith Enck was mentioning that fossil fuel companies see plastics as their plan B as the demand for petrol and fuel goes down. Do you agree with this?
Yes, one of the trends we are seeing is that demand for plastics and other petrochemicals is one of the key drivers for oil and gas now that the markets for petrol and diesel are decreasing. More and more, we see oil firms investing very strategically, either themselves or in partnerships with plastics and petrochemicals producers. So they for sure seem to be betting on this as their plan B.
Earlier, we also heard about the extensive emissions that occur during the production of plastics. I know you use this concept of carbon lock-in in your work. Could you explain what carbon lock-in is and how this relates to the projected emissions from plastics?
So carbon lock-in is a concept that connects the idea that technologies are used for specific purposes, but they are also strongly linked to regulations, institutions, and practices in society. So technologies become so embedded and they become part of our infrastructure for everyday life. So once we have created this path for how we use plastics, it's very hard to diverge from it. Instead, it becomes self-reinforcing. And the foundation for the carbon lock-in in plastics is that plastics are almost exclusively produced from fossil fuels. So we are locked in to using fossil-intensive plastics in many, many different ways in our everyday lives.
Given the problems we've heard associated with plastic, do we need to get rid of them altogether?
I don't think that we should say that we can get rid of them. That would be foolish, knowing that plastics are useful in many applications. However, we need to think carefully about where we use plastics to reduce demand growth. We need to think where we really need these properties that plastics have. We need to think about what is it that we really want to use these materials for, knowing that there are often many choices, whether those be plastics, steel, other metal, which one would be most sensible to use in that particular application, and which one would have the lowest environmental and climate impact.
Could you give some examples of sensible or essential applications where we still need plastics going forward?
Yes, I think it's fair to say that it's difficult to see modern healthcare, for example, completely without plastics. But there's still the question to what degree we want to use plastics. How much of the equipment that we use has to be single use and how much can be reused, sterilized, etc.
Earlier in the show, we heard from Lee Bell about how plastic recycling might not be a suitable solution on its own to the plastic problem. Do you agree with this? And if so, what else should we be doing?
Yes, the recycling systems that we have developed and deployed so far are not suitable for dealing with plastics in the way that we use them today. So just saying that we should scale up the recycling that we have, that will not be sufficient. That's quite clear. Instead, we really need to think about where and how we use plastics from the start. I think we should think about our consumption practices and how they relate to this exploding use of plastics. For example, textiles, where our consumption of clothes has exploded in the recent decades, and that is to a very large degree connected to the availability of cheap polyester. So what do we really need to consume in terms of fast fashion, for example? On the other hand, I think it's also very important to see that this is not something that we are going to solve at the individual level. Rather, we really need to think about how to put pressure on the system.
And if you had one recommendation for what individuals can do to put pressure on the system, what would it be?
We should all recycle our consumables, but that's really just the bare minimum. So what we can do instead is to get organized in different ways to put pressure on policymakers, decision makers, larger firms, that they should make the necessary changes on the higher level for how we really use plastics.
Just to end, what do you see as the future of plastics?
Unfortunately, what we are seeing is that the industry is still to a large degree betting on an unabated use of plastics. And if we don't challenge that, it's likely that we will see this perhaps even quadrupling in demand for plastics, and that it would be based on primarily fossil sources, with recycling being a very niche, marginal activity. However, there is also the opportunity that we can change it. We do have agency and we can shape our future in a different way than just extending these unsustainable patterns from the past. But that does require action on many levels. So in an ideal scenario, we are able to transform the way that we produce plastics to primarily use recycled plastics through different forms, but also then producing some virgin plastics from more sustainable sources.
I'm at the checkout now, and I can't believe how much plastic I've managed to accumulate. And just to think of all the emissions associated with this plastic. But as Frederick said, I can't instigate significant change by just me buying loose vegetables. So I'm going to buy my ingredients for tonight's dinner and recycle the packaging when I get to it. Frederick has inspired me to look at how I can help instigate real change and reduce plastic production at the source. I'm going to try joining a campaign, pushing for limits on plastic production, writing to my local MP, and chatting through what I've learned with friends and family members. Now that I've got a plan, I can finally enjoy my spaghetti. Oh no, it's 7 o'clock and I haven't even cooked yet. Time to get to it.
Now, just before we go, it's Chris here jumping back in to ask you a favour. Around this time of year, and it is Giving Tuesday today, we remind everyone listening about our fundraiser that keeps The Naked Scientists going. Some of you very kindly support us with regular one-off contributions that help us to pay our hard-working staff and keep us equipped and our website running so we can continue making this programme. So if you do enjoy this show, you haven't supported us yet, but you would like to show your support going forward and keep us going, we've made it really easy and secure for you to make a donation. Please go to nakedscientist.com/donate. That's nakedscientist.com/donate.
Well, that's it for this week. A big thank you to Werner for signing for helping to put the show together. Next week, we're back at it again, answering those questions that you've been sending in. And oh boy, have we got a great lineup for you. We'll be joined by those with an understanding of the deep sea, exoplanets, and artificial intelligence. And get this, we've also nabbed a science rap superstar. So if you need to get your scientific groove on this festive period, it's definitely not to be missed. The Naked Scientists come to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Harry Lewis. Thanks for listening. Until next time, goodbye.